So I'll just draw some diagram. All of you so far understood what is a point source, what is an isotropic radiator? Okay. This angle is suppose is your phi. This is your point source A1 and this is your point source A2. So you already understood what is a point source. Point source doesn't have a specific shape and size, and this is used to find out the array of 2 point sources. We use this concept of point source. We have also understood what is an array of an antenna, what are the properties of an array of an antenna, and we have also understood why array of antennas are used in the practical scenario. So I will keep this as point P with a distance far off point source A1 and A2. At this point P, we need to find the total electric field due to point source A1 and A2 combined effect. I have to find. This is one antenna 1, antenna 2, which are treated as point source. So the radiation pattern at point P in terms of electric field and the radiation pattern, we are going to find out through this derivation. I hope it is clear for you. Assume this line makes a perpendicular here. So this will be your d cos phi distance. This distance between the point source A1 and A2, I am taking as d. Okay, so this will be your d cos phi, this distance, this one. So suppose from point source A1, the distance is R1 to point P, and from point source A2, this is distance R2 from point P, point A2. So that is the distance point P. This is very far off point. So these are almost like parallel lines. So what happen is, if this point P is nearer to R2 as compared to R1, the electric field from A1 will reach d cos phi times. It has to take more distance as compared to A2. That is why this term d cos phi is your phase shifter, which is considering, which we are considering. As we do the derivation, you will understand. At the end of the class, if you are not able to understand for any reasons, please ask me. Consider, okay, sorry. Consider point P far away from array of 2 point sources A1 and A2. A1 and A2. The distance between point P and the point sources A1 and A2 are R1 and R2. That is, between A1 and point source P, the distance is R1, and the distance between A2 to point source P is distance R2. Okay. R1 and R2 are very large as compared to D. They are very large as compared to D. Therefore, we assume R1 is equal to R2 is equal to R. Okay. the radiation from point source A2 will reach point P earlier than from point source A1 because of path difference. Because of path difference. Okay. Path difference is nothing but your d cos phi, which I have shown in the figure, in terms of wavelength, in terms of wavelength, it is d cos phi by lambda. Okay. Now we are doing the derivation. Please observe very carefully. Now I define, sorry, not I define, we define. Now we define phase angle psi as equal to 2 pi into path difference. 2 pi into path difference. So that will be your 2 pi d cos phi by lambda. 2 pi into d cos phi into lambda. So this phase angle psi is 2 pi d cos phi by lambda radians. Now propagation constant beta is defined as 2 pi by lambda. Okay, propagation constant beta is defined as 2 pi by lambda. This is also called as phase shift. Why it is known as propagation constant is for a particular wavelength, this beta is constant. So if you call this as equation 1, so if you substitute in the above equation, you will get psi is equal to beta d cos phi, this many radians, where beta is your 2 pi by lambda, where beta is your 2 pi by lambda, this many radians. Now we'll find out the electric field at a distance point P. In that you have case 1. This is all I have put as case 1, so don't get confused between this case and that case. So I'm finding equal magnitude and equal phase. In this case 1, what I will consider is, I will consider your point source A1 as the source and then find out the electric field at point P. In your case 2, I will take a reference point at the center and find the electric field at point P, and we will find out the difference. If I take the reference point as the source itself, what happens? Case 1. In this case, okay. In this case, the reference point is taken as the source A1 itself. A reference point is taken as the source A1 itself. So what happens here is the total electric field, E total will be your electric field due to source A1 plus electric field due to source A2, where E1 is the electric field due to source A1 and E2 is the electric field due to source A2. A1 and A2 are 2-point sources. So I can write E total is equal to E naught e raised to the power j psi by 2 plus E naught e raised to the power 1 will be minus j psi by 2 and j psi by 2. So this will be, I can take out E naught outside. Take out E naught outside. So you can rewrite this equation as well. Sorry, one small correction. I got just a little confused with these equations. When you are taking the this is reference point at the center of the array. So when you are taking the reference point at the source 1 itself, so what happens here is the first source will not have any kind of phase shift. So that is a very important concept which you are required to know, is that the first source A1 will not have any kind of phase shift. So that is plus your E naught e raised to the power j psi. This is your source A2. So your entire phase shift will go to your source A2. So this I can rewrite this as E naught 1 plus e raised to the power j psi. Okay, I will multiply and divide by 2. So this will be 2 E naught 1 plus e raised to the power j psi, okay, divided by 2. So I will multiply and divide by 2. So what another circus I can do is 2 E naught. I will take e raised to the power j psi by 2 outside the bracket. So here I will get e raised, sorry. So I will get here e raised to the power minus j psi by 2 plus e raised to the power j psi by 2. If you multiply these two, you will get 1. So that divided by 2. So what happens here is, this will be cos of psi by 2, e raised to the power minus theta. This will be like e raised to the power, we know that e raised to the power minus j theta plus e raised to the power j theta by 2 is cos theta. In this case, theta in this case theta is equal to psi by 2. So what happens to the above equation is, I'll call this as some equation number. So this is your equation number 1. So I will call this as equation 2. Okay, I'll call this as your equation number 2. So theta is equal to this one, so you'll get as cos theta is equal to psi by 2, so you'll get cos psi by 2. So your total electric field E total will be equal to 2 E naught e raised to the power j psi by 2 cos of psi by 2. Okay, so where 2 E naught is the amplitude of the total electric field, where 2 E naught is the amplitude of the total electric field. So the above equation will reduce to Et is equal to 2 E naught is equal to amplitude. I will make this as equal to 1. 2 E naught maximum value is 1. So I will get E total is equal to e raised to the power j psi by 2 into cos of psi by 2. E raised to the power j psi by 2 into cos of psi by 2. So this can be written as cos psi by 2 at an angle psi by 2. This phase term. This is your derivation of your total electric field when the reference point is taken as the center of the array. So I'll call this as your equation 3. So your equation 3 represents total electric field when the reference point is taken at the array point 1 itself. Array point E1 itself. Okay, now if I have to draw the vector diagram for this, I will have I hope you know the vector notation of drawing. This is your electric field E1 is equal to E naught, that is your source 1. This is your electric field E2, that is equal to E naught e raised to the power j psi, that is your source 2. This is your resultant electric field. This is your resultant electric field. This is your origin O. I hope you understood this. So you have some kind of phase shift if you take the reference point at the source 1. The reference point at the source 1 means I'm once again repeating. This I am taking as a reference point. So this A1 will not have phase shift with A1. A2 has a phase shift with A1. So this A2 which has a phase shift with A1 is nothing but your e raised to the power j psi. This is your phase shift part. This is your phase shift of A2 with respect to A1, that e raised to the power j psi. So your total electric field, once again repeating, E naught is the amplitude. So A1 will have no phase shift. This is A1. This is the second one, e raised to A2. So this will have a phase shift of e raised to the power j psi. Okay, so when I am doing the derivation, I'll do 1 plus e raised to the power j psi, then multiply and divide by 2, then take e raised to the power j psi by 2 outside the bracket and then do, which I have just done. So I hope understood. Reference point I am taking at the source 1 itself. That is what is the derivation for. Now in this you have case 2 where reference point is taken at the center of the array. The reference point is taken at the center of the array. Yeah. This is your point source A1. This is your point source A2. This is the center point here. Something it is looking like a center point. So this is your distance point P. There I am finding the total electric field. So this angle, if it is psi, this angle will also be psi. Okay. This is your total distance D. This is your total distance D. D by 2. D by 2. Okay, two distance here, D by 2, D by 2. I'm taking, this is your reference point at the center of distance d by 2 and d by 2. What happens now is this phase shift e raised to power j psi will be equally divided between these two reference point a1 and a2. Okay, so the total electric field E total again is E1 electric field E1 due to point source A1 plus vector addition of electric field E2 into point source A2. So what happens here is, so you get here E naught e raised to the power j psi by 2 plus E naught e raised to the power minus j psi by 2. One side you take positive, one side you have to take negative to balance both things. Okay, so this will be, I will take E naught outside. This will be e raised to the power j psi by 2 plus e raised to the power minus j psi by 2. You multiply and divide by 2. So what happens is 2 E naught. This will be e raised to the power j psi by 2 plus e raised to the power minus j psi by 2 divided by 2. So this will be cos theta e raised to the power theta minus plus e raised to the power minus theta by 2. That is be a cos theta. So your total electric field Et. So your total electric field Et will be nothing but 2 E naught cos of phi by 2. Sorry, cos of psi by 2. This is your derivation for your total electric field when the reference point is taken at the center of the array. So this is the vector diagram for that. This angle is your psi by 2. This angle is your psi by 2. So your E1 is equal to E naught e raised to the power minus j psi by 2. E2 is equal to E naught e raised to the power j psi by 2. This is your total electric field E. This is your total electric field E total. Now, one major difference that you will find between your equation 3 and equation 4 is when the reference point is taken as the center of the array, you don't get this angle psi by 2. So 2 E naught is the amplitude. So if 2 E naught is equal to 1 like the previous case, so I'll get E total is equal to cos of psi by 2. E total is equal to cos of psi by okay. Now another thing we have to find is the maxima, minima, and the half power point directions for this. To find the maxima direction, we have found the electric field. Now maxima direction, minima direction to find the radiation pattern. Okay. To find the condition for maxima, we equate the phase part of the above equation to the maximum value, that is cos of psi by 2. I equate to the maximum value, that is 1. Cos of psi by 2 is equal to 1. So okay, we know that psi is equal to beta d cos phi, where beta is the propagation constant given as 2 pi by lambda. D is the distance, we'll assume as equal to lambda by 2. Okay, so what will be your psi value now? Psi is equal to 2 pi by lambda. D is your lambda by 2 cos phi. So 2 will get cancelled, lambda will get cancelled. So psi is equal to pi cos phi, and your psi by 2 is equal to pi by 2 cos phi. Pi by 2 cos phi. So that is your psi by 2. So now what I have to substitute in this equation, cos psi by 2 equation. So your cos psi by 2, cos of psi by 2 is nothing but cos of pi by 2 cos phi is equal to plus minus 1, or this is all your mathematics. Pi by 2 cos phi, pi by 2 cos phi is equal to cos inverse of plus minus 1. Okay, cos inverse of plus minus 1. So if you solve this, I can write as, this is maxima condition. So pi by 2 I can write as cos phi maximum value is equal to 0. But pi by 2 cannot be equated to 0. Therefore, cos phi max should be equal to 0, or your phi max should be equal to 90 degree or 270 degree. This is your maxima condition. This is your maxima condition. Next, you have to find minima condition and half power point direction. Next, this is your minima condition. In your minima condition, what I will do is I will equate cos of psi by 2, I'll equate it to 0, or cos of pi by 2 cos phi, I'll equate it to 0. Same thing, like beta d cos phi will be a pi by 2 cos phi. So your pi by 2 cos phi, this is minima condition, will be equal to cos inverse of 0. This is equal to pi by 2. Okay. So this will be, what is this? Pi by 2 cos phi minimum will be cos inverse of 0. Actually, you have to write this as equal to plus minus n can take any values 2n plus 1 pi by 2. So if n is equal to 0, then it becomes equal to pi by 2. It comes back to the same value. So I can write this as, this will be plus minus pi by 2, plus minus, so pi by 2 cos phi minimum is equal to plus minus pi by 2. So pi by 2 will get cancelled. You will get cos phi minimum is equal to plus minus 1. Okay. Or your phi minimum value will be a 0 degrees or 180 degrees. Phi minimum value will be your 0 degrees or 180 degrees. Next, you have to find what is known as half power point direction. Half power point direction, that is also known as HPPD, half power point direction. Okay, in case of this, I'll equate cos of psi by 2 is equal to plus minus 1 upon root 2 for your half power point direction, or cos of, that is your beta d cos phi whole thing. If you again do, you will get pi by 2 cos phi, pi by 2 cos phi is equal to plus minus 1 upon root 2. Okay, so this will be pi by 2 cos phi, half power point direction will be cos inverse of plus minus 1 upon root 2. Okay, so plus minus can be removed. So this will be pi by 2 cos of phi half power point direction, this will be pi by 4. So this pi will get cancelled. Your 2 ones are 2 fours are. This will be half. So cos of pi half power point direction. This will be half plus minus. So your pi half power point direction will be 60 degrees or 120 degrees. That is why we are doing that plus minus 1. Finally, you have to draw the radiation pattern. For drawing the radiation pattern, I'll draw the x and the y axis. Draw one H shape, something like this. Okay. Try to draw H shape here. So that is your radiation pattern. How that is how it will come. Something like this. So this is your phi max value. This is your phi max value. That is your 90 degree. This is your phi minimum value. Phi minimum value, that is your 0 degrees or 180 degrees. This is your 270 degrees. This is also your phi max value. Your half power point direction, phi of half power point direction will be 60 degrees. Okay, please look at this. This the maximum radiation will occur at 90 degrees or 270 degrees. In your minima condition, your radiation will occur at 0 degrees or 180 degrees, and your half power point direction is 60 degrees or 120 degrees. So if you draw, it will be a H shape, exact H shape with half power point direction at 60 degrees or 120 degrees. This is your 120 degrees this side. So that is how your radiation pattern will be coming. I hope you. Okay, there's one more small term known as the array factor. It is the ratio of magnitude of the resultant field to that of maximum field. So your array factor is your total electric field divided by maximum electric field.